Good evening, everybody. Welcome to Chem 1105 with your host, me, Dr. White. Tonight, I'll be doing the review for test number 3. And let me just open up something. And let me check to make sure you're seeing it. You are. I put out this announcement on the 3rd of April, a while ago, like 6 days ago. And let me just remind you, this Thursday, I will be giving test number 3 online, and about 8 o'clock or earlier, I'll send out an email with a password to open up the password protected PDF file of test number 3. And you'll have until Friday, 8 p.m. to finish test number 3 and upload it as a single PDF file to Blackboard. Now, test number 3, and I'll be going over this tonight, covers chapter 6, which is gases, and chapter 5, part 2, which is solutions. And if you notice, there's 48 points on gases, 57 on solution. That adds up to 105. So there's five bonus points. You'll need a scientific calculator, and I hopefully you've read the rest of this. All right, let me remind you, on the beginning of test number 3, it will say, please use significant figures for all calculated answers. And it'll also say, please use 3 significant figures for all atomic masses. And you learned how to, or atomic weights, really. And you learned how to do that for test 2, I hope. Now, in the lecture folder of Blackboard, you'll find a file called Important Information Test Number 3. And in the past, years ago, before I changed my approach, you would have to have memorized all this. Well, guess what? Good news. This will be the last 2 pages of the test number 3. So you don't have to memorize this stuff, but you will have to know how to use this. So let's get going. Again, that's in the lecture section of D2, wrong school, Blackboard. The other school I teach at, their computer system is called D2L. Now, in also the lecture section of Blackboard, you will find test number 3 review, both as a Word document and a PDF file. And so what you're seeing now will be available to you on Blackboard. All right, let's get going. Let's talk about gases. First thing is, one of the important measurements of gases is pressure. And you should know 1 millimeter mercury equals 1 torr. And there's a mistake here. That should be mm. Sorry about that. Nope, actually, that should be torr. Oops, it's right on the important information. It's wrong here. But anyways, 760 torr equals 760 millimeters of mercury equal 1 atmosphere, ATM. And you should know how to convert from one to the other. And let me open up something that I don't have opened up. And if I were to ask you, how many ATM atmospheres is 425 torr? And as I've taught you all semester, what are you being asked to find? Atmospheres. What are you given? Torr, 425. And this is the only number we have to start with, so I will. And if I had some ratio, what units do I want my answer to be in? Well, we figured that out. ATM. And now it's time to use your good buddy, your good friend, unit analysis. Whatever I'm trying to get to, the units go on top of the ratio. Whatever I'm trying to get rid of, the units go underneath. And now write them in. And where do we find a relationship between torr and atmospheres? Well, if we go to look at important information, test number 3, 760 torr equal 1 atmosphere. And remember, when you have A equal to B, there are two ratios you can always have, A over B, and they're not equal, they're different ratios, and B over A. So 1 atmosphere, 760 torr. 1 atmosphere, 760 torr. And notice torr cancel out. Anything divided by itself equals the number 1, meaning it's gone. I'm left with atmospheres. Now 1 and 760 are part of the definition, so they're exact numbers. This is 3 significant figures. And when you do a multiplication division, your answer should have the same number of significant figures as the number that has the fewest. So in this case, the only number we're going to deal with that isn't an exact number is 3. So now, turn on my calculator, clear it. 425 times 1 is 425, divided by 760, 760. And my calculator gives me this number. Well, as I said earlier, on test number 3, it'll say, please use proper significant figures for all calculated answers. So this needs to be 3 significant figures. Keep the 5, keep the 5, keep the 9. Use the next number 2 to round off. Is that 4 or less? Yep. So that means I drop all this. And the correct answer using significant figures is this. So don't forget to use your good buddy, your good friend, unit analysis. By the way, I'm going to take a timeout for a public service announcement from the manager and me. On test number 3, like test number 2, it pays to show your work. If you write down an answer and show nothing else and it's wrong, you'll get 0 points. And if you show all your work and you make a mistake here or something, I can give you partial credit, not 0 points, unless you get it all wrong, and I hope you don't. So it pays to show your work. All right, just a reminder, in gases we use Kelvin, K, but all of the thermometers I've ever seen in digital ways of measuring heat temperature has been in Celsius in science. So you have to convert this to Kelvin. And we did that in test one, but here's the formula again, so you don't have to remember it. Now, next I started talking about the gas laws. And gas laws are mathematical relationships that are always true. And the first one is Boyle's law. P1 times V1 equals P2 times V2. P1 is the initial pressure. V1 is the initial volume. P2 is the final pressure. V2 is the final volume. Now, in the problems I will give, or anybody would give, you're going to be given 3 of those 4 variables. And the fourth one you have to calculate using Boyle's law right here. And if you look on your screen, I have one of the practice problems. Let's do number 6. If a balloon has a pressure of 655 torr and a volume of 1.894 liters, that's what L is, what is the pressure of the balloon if the volume is increased to 5.133 liters? Well, what do? First of all, what are you being asked to find? A pressure after initial pressure, which would be P2. The initial pressure, P1, is 658 torr. The initial volume is V1, 1.894 liters. And when you increase the volume, the final volume of that balloon will be 5.133 liters. Well, how do I proceed? Well, if you notice, all you have is pressure and volume. Whenever you see a problem with only pressure and volume, this will be 8 or 10 points. Ooh, yes, that many. You'll say, I need to use Boyle's law. P1 V1 equal P2 V2. I almost got ahead of myself, the next law. Now, we want P2 alone on one side. And anything divided by itself is number 1, it's gone from that side. So if I want to get rid of V2, because I want P2 alone on one side, because that's what I'm solving for, I'll divide this side by V2. V2 over V2 is 1, times P2 is P2. But whatever I do to one side, I have to do to the other. Divide by V2. So now we have V1 times P1 divided by V2 equals P2, the final pressure, which is what we're trying to find. Now, you don't have to do it, but I like to rewrite it. And now, since we took the time to figure out what is P1, V1, V2, I can just put them in. Now, once again, use your good buddy, your good friend unit analysis. Notice liters divided by liters, that unit is gone. We're left with torr, which is a pressure. So we set it up right. Now, notice 658, 3 significant figures. 1.894, 4 significant figures. 5.133, 4 significant figures. When you multiply and divide, your answer should be the same number of significant figures as the number you're multiplying and dividing with the lowest significant figures, this case 3, and my answer is 3 significant figures. I see a question. We'll get to that in a little while, Flora. But anyways, that's PV, P1 V1 equals P2 V2. And how did I know to use that? Because the only variables we were dealing with were pressure and volume. And that immediately tells you Boyle's law, P1 times V1 equals P2 times V2. Now, the next law, and remember, I'm not going to have Charles' law on the test. That's my gift to you. Shh, be quiet. Don't tell anybody I'm being nice. All right, let's talk about the ideal gas law. And in all chemistry, this is probably my favorite mathematical formula. This is fun. Now you know I'm a chemist. All right, and the ideal gas law is PV equal nRT. P is pressure, but for this to work, it has to be in atmospheres. V is volume, and that's always in liters. N is the number of moles. T is the temperature in Kelvin, and R is the universal gas law constant. And for my class, you use 0.0821 atmospheres liters per mole K. Now, this universal gas law constant R is a calculated number. I don't know how long ago it was. I think I saw a website or that it was trustworthy. They had R to something like 15 significant figures. Why you'd ever need that, I don't know. But for my class, R is 3 significant figures. All right, let's take a look at 2 problems. Let's first look at number 10. And I had a little fun with this. If you burp 86.75 grams, which is not realistic, but I still wanted to have some fun with this, of carbon dioxide, CO2 gas at 544 millimeters of mercury and 34.6 degrees C. What's the volume of your burp? Now, first of all, what are we trying to find? V, volume. We're working with a gas. We're given the weight. We're given the pressure. How do we know? Because you know mmHg, millimeters of mercury, is pressure. We're given the temperature, and you'll be given R, the universal gas law constant. Now, how did I know to use PV equal nRT? By the way, I forgot to put here 15 points. I forgot to put 15 points. But anyways, nothing is changing. You're dealing with a gas. Immediately that tells you you're going to need PV equal nRT. And on important information, test number 3, like I said years ago, students who are taking this test would have to memorize this. This will be given to you. The ideal gas law, PV equal nRT. P is in pressure, atmosphere. V, volume in liters. N is the number of moles. T in Kelvin, temperature. And here's the universal gas law constant, 0.0821 atmospheres liters mole K. So what do we solve for? Volume. So how do we get volume V alone on one side? We have to get rid of P, the pressure. How do you get rid of something? Divide by it. Anything divided by itself is the number 1. But whatever you do to one side, you have to do to the other. And I did. And P over P is 1 times V is V, and the other side is equal to nRT over P. But these units that you put into these values have to be in the right units. So first of all, N is moles, which I have right here. And you have a weight. And from test number 2, almost said the wrong test, you know 1 mole of a compound equals the molecular weight of that compound. Good news, in case you forgot that. I'm looking at the wrong thing. I'm looking at the right thing. You notice important information, test number 3, 1 mole of a compound equals the molecular weight of that compound in grams. And the molecular weight of that compound is the sum of all atomic weights. And hopefully you learned that for test 2 because you'll need it for test 3. So we have 86.75 grams of CO2, 1 mole of CO2 for the molecular weight of CO2. Because you want to get the moles, use your good buddy, your good friend, unit analysis, whatever we're trying to get to goes on top of the ratio. Whatever we're trying to get rid of, grams of CO2, goes underneath. And this is 1 mole, and this should be the molecular weight. And the molecular weight is the sum of all atomic weights. For carbon, there's 1 of them. And remember, use all atomic weights, the 3 significant figures. And that's 12.0. 1 times 12.0 is 12.0. There are 2 oxygen. Each oxygen, it looks like a 6, but that should be a 0, are 16.0. 2 times 16.0, 32.0. Add them up. You get 44.0. Remember, you get the same number of significant figures to the right of the decimal as the number with the fewest significant figures to the right of the decimal. In this case, this is 1, 1, then you get 1. And here we have 4 significant, exact number 3. You round it off, your answer should have 3 significant figures. So we now know N is 1.97. Next, R we're given. T is temperature in Kelvin. And remember, in case you forgot, Kelvin equals degrees C plus 273. So temperature in degrees C, centigrade, Celsius, 34.6 plus 273 gives you this number, 307.6. And finally, pressure. Now, pressure has to be in atmospheres. And you should know that 760 torr and 760 millimeters of mercury equal 1 atmosphere. So we have 745 millimeters of mercury. We want to get the atmospheres. Use your good buddy, your good friend, unit analysis. Whatever we're trying to get to goes on top of the ratio. Whatever we're trying to get rid of goes underneath. And where do we get these numbers? 1 atmosphere is 760 millimeters of mercury from the important information, test number 3. I gave it to you. Now, this is 3 significant figures, exact number, and my answer here is 3 significant figures. And now I have N, R, T, and P. I put them in. Now, this is one of those you can either round off at each step, and remember, I'm a round off at each step person, or wait till the end. And I calculate for my test both ways because it's not right for me to force you one way or the other, even though I like rounding off at each step. So put in N, 1.97 moles, R, universal gas law constant, the temperature in Kelvin, and the pressure in atmospheres. Common mistake, students put in the pressure in millimeters of mercury or torr. And it's wrong, or they don't convert temperature into Kelvin, or they use grams instead of moles. So make sure you have the right units for these right here, and you can find that important information. Three significant, three, four, three. My answer is three significant figures, and either you round off at the end or each step, it's the same number. Now, this is a fictitious number because I don't think your lungs can hold almost 70 liters of CO2. You know, those 2 liter bottles, you'd need 35 of those for that burp. Ooh, almost. All right, now I have a request to do number 9. What is the weight of 5.77 liters of oxygen gas at 102 degrees C and 678 torr? So we're trying to find a weight, grams of O2. We're given a volume, temperature, pressure, and you'll need the universal gas law constant. Now, if you think about it, there's nothing I can go from those numbers to grams. However, in 2 steps, I can take PV equal nRT and solve for N moles. And then second step, take moles and convert it into grams, which you learned for test number 2. So for test step 1, PV equal nRT, you want moles along and alone on one side. So we have to get rid of RT, divide by it. Whatever we divide by one side, we do on the other. R over R is 1, T over T is 1. So we're left with N equal PV RT. And I just rewrote it because I like to do that. You don't have to. Now, pressure has to be in atmospheres. And here like I did earlier, I converted a torr to atmospheres. Temperature has to be in Kelvin. So it's degrees C plus 273. Here's degrees C at 273. I now have Kelvin. And volume has to be in liters, and I gave it to you in liters. Put the numbers in, and you get, this will all be 3 significant figures, 0.170 moles of oxygen. But we're trying to get to grams of oxygen. So I need a second, excuse me, water time. Boy, these gas problems are thirsty stuff. But anyways, second step, I have 0.170 moles of oxygen. I want to convert it to grams of oxygen. Remember, use your good buddy, your good friend, unit analysis. Whatever we're trying to get to goes on top of the ratio. Whatever we're trying to get rid of goes underneath. And remember, from important information, test number 3, 1 mole of a compound equals the molecular weight of that compound, and the molecular weight of that compound is the sum of all atomic weights. In this case, oxygen gas, O2, has 2 oxygen. Each oxygen is 16.0. Let me open up something. Hang in there. Just to remind you, underneath the chemical symbol of this periodic table, which you'll be given for test number 3, notice I have 15.999, round that off at 16, the 3 significant figures, 16.0, and that's the atomic weight of oxygen. And now oxygen 16.0, there are two of them, 32.0. 32.0 goes there, one goes there, moles cancel out, I'm left with grams, and that's how you do it. But I would highly recommend you look at number 10, and why don't you also on your own look at number 11. Hint. All right, one other thing I should mention about the ideal gas law. The ideal gas law tells you when to check the pressure in your tires. In your tire, unless you get a flat, and then all bets are off, and hopefully you don't. The volume, moles, and R are always the same in your car tire. What can change is the pressure and the temperature and the pressure. In winter, what happens? It gets cold. The temperature goes down. And if you watched the video, I talked about how I came out one night or one morning after it had been not wind chill, actual temperature about 22 below, check my car and drive it around more for the battery. I saw all the tires look flat. It took me about, a little less than a second to realize, no, they're not flat. PV equal nRT. It's winter, the temperature really dropped, therefore the pressure dropped. And in the winter of 95, we had a tremendous heat wave in Chicagoland. And if you were on the expressways, you saw a lot of cars and trucks pull over because their tires blew out. What happened? Oops, wrong thing. Summer temperature goes very high, and therefore the pressure of your tires can go high. And you should check them so that if it gets real hot, they might, like a balloon being blown up too much, pop. And that happened. Oh, all right. The last thing is Dalton's law of partial pressures. And I went through problems like this. The sum, the total pressure of a mixture of gases is the sum of the partial pressures of each gas. P total, the total pressure of a mixture of gases, is the sum of the partial pressures, P1, 2, 3. Partial pressure is what would be the pressure of that gas if it were alone in that mixture, which no longer be a mixture. Now, a couple other things I talked about was boiling point of a liquid. And that's where in a liquid, warning, warning, danger, artwork, don't laugh too hard. I have a beaker with water over a Bunsen burner, and this is the flame. I told you I'm not an artist. Eventually, you'll see bubbles form and they rise to the surface. And those bubbles are water vapor, water in a gas phase. And any gas has a pressure, and the gas here, when that pressure equals the atmospheric pressure, the temperature of the liquid is the boiling point. Now, if you were to go to Denver, this actually happened to me, and had friends there, they no longer live there, but they did a long time ago. If you go there, you'll find out the boiling point of water is lower than here in Chicago. Why? Denver is the mile-high city, and it's at a higher altitude. And as you go up in altitude, the atmospheric pressure goes down, so you need less heat to get the vapor pressure of the boiling water equal to the atmospheric pressure, because it's lower. And that's why the boiling point goes down when you go to a higher altitude, which I have here. All right, next I talked about solutions. And you should know a solution is a mixture of two or more substances which each retain its own chemical identity. And in a solution, the component present in the greatest amount is called the solvent. All other components are called solutes. Now, I also talked about something that looks like a solution, but it's not, and that's called the colloidal dispersion. And that's where there's particles, small particles of one substance suspended, not dissolved, in a other material. And how can you tell that? Oh, it's time for Dr. White to show off one of his fancy flashlights. This is a flashlight made by Hank Wang in China, who's probably the premier flashlight builder in the world. It's one of my hobbies. You can see a bunch up there. And if you have a regular solution, light will go through it. If you have a colloidal dispersion, because of small particles, no light goes through it. Not that my hands, but you get the idea. If you were to hold up a glass of milk, the light wouldn't come through. By the way, is this a cool light or what? Watch this. Oops, too low. Both red and white. Got to show on my flashlights. Yay. And you should know examples of colloidal dispersions in our daily life. One is milk, another one is your blood, and the third one, latex paint. Mustard and ketchup would also fall under that. Now, next I talked about an important concept called light dissolves light. And that means things that are polar or like solutes are soluble in like solvents, which we break it down. Polar solutes are soluble in polar solvents. Non-polar solutes are soluble in non-polar solvents. And if you mix the two together, they're not. And my lecture, what's the most polar solvent? Water. Another one, alcohol, or any small alcohols, and salts like sodium chloride. What's nonpolar? Vegetable oil, Vaseline, also known as petroleum jelly. Gasoline is nonpolar. And if you took water and vegetable oil, like oil, vinegar, or dressing, mix it up, they separate because light dissolves light. One's polar, one's nonpolar. Now, there's certain definitions I asked you to learn. The solubility of a solute in a certain solvent is the maximum amount of solute that will dissolve in a given solvent. Saturated solution contains the maximum amount that can be dissolved under the conditions at which the solution exists, like temperature and pressure. Now, dilute solution is a solution that contains a small amount of solute relative to amount that could dissolve. And more than once when I was younger and not happy about it, I was in a bar And I asked the bartender, boy, this is a really dilute drink. He wasn't happy. I wasn't happy. Never went back to those bars again. Now, a concentrated solution contains a large amount of solute relative to the amount that could dissolve. And finally, the most important, an aqueous solution is a solution in which water is the solvent. And I'll show later on, it's designated by bracket AQ, close bracket. Now, when you make a solution, how much solvent and solute are there? Well, that's called concentration. And there are different ways of measuring concentration. In my class, the only one I'm going to ask you to learn is molarity. And molarity, which is designated by capital M of a solution, is the ratio, and I'll never ask you what's the definition of molarity of a given number of moles of solute per liter of solution. But you should know molarity equals moles of solute per liter of solution, but 1 liter of solution is 1,000 milliliters, and this is the most important thing. Know this. Example, so what does this mean? And what is the solvent? Well, as soon as you see capital M, that's molarity. And the number in front tells you it's 1.35 moles of KBr, potassium bromide, per 1,000 milliliters of solution. Now, what is the solvent? Remember, I just mentioned bracket AQ, close bracket means aqueous, and that means the solvent is water, H2O. And it's important to know whenever you see the capital M number before and a formula afterward, it means this, moles of a substance per 1,000 milliliters. Now, when it comes to molarity, remember it's moles of solute per moles, 1,000 milliliters of solution. And here's chapter 5, part 2, solution practice problem answers. That's in Blackboard. And let's look at number 8. How many moles of NaCl, sodium chloride, are in 125 milliliters of a 3.45 capital M NaCl? And as you've learned by now, I like to put a question mark. Then what am I being asked to find the units? Moles of NaCl. What am I given? 125 mils and this number, 3.45 capital M NaCl. Well, the only number I have to start with is 125 milliliters. What units do I want my answer to be? Moles of NaCl. So now it's time to use my good buddy, my good friend, unit analysis. Whatever I'm trying to get to goes on top of the ratio. Whatever I'm trying to get rid of, the units, milliliters, go underneath. Now, if we come over here, 3.45 capital M, what does that mean? Excuse me. And capital M means molarity. And that's 3.45 moles of NaCl per 1,000 milliliters. And that's where we get these numbers. Now, when you're doing a multiplication division, you get the same number of significant figures in your answer as the number with the lowest significant figures you're multiplying and dividing by. And here, 3 significant figures, 125, 3.45, 3 significant figures. Now, the 1,000 is part of the definition, so that's an exact number, 3, 3. Our answer is 3 significant figures. Now, there's something that I call the molarity two-step problem. And the first step, you have to convert milliliters to moles and then moles to grams. And this kind of calculation is how we make up stock solutions, either in a lab, or I've done this calculation in a chemical plant, where instead of making a few milliliters, we made like, I don't know, a couple hundred gallons. I had to do the calculation. We're staying away from English units, gallons in this class, but anyways, let's look at an example of that. All right, number 11, let me make sure you can see this. And you can. The question is, and I don't know, maybe, hold on one sec. Now it's no longer blue. How many grams of NaCl, sodium chloride, are needed to make 345 milliliters of the 6.789 capital M NaCl solution? So what are we trying to find? Grams of NaCl. What are we given? Milliliters, and this number, 6.789 capital M NaCl. Whenever you see the capital M, that means molarity. What this really means is 6.789 moles of NaCl per 1,000 milliliters. Now, there's no way I can go in one step from milliliters to grams. You can't. You need 2 steps. And once again, important information, test number 3. We have molarity 2-step problem, milliliters to moles, first step, then moles to grams, second step. So first step, we have 345 milliliters, and we want to get to moles of NaCl. And we'll use our good buddy, and my good friend, hopefully by now yours too, unit analysis. Whatever we're trying to get to goes on top of the ratio. Whatever we're trying to get rid of goes underneath. Where do we get these numbers? From the molarity, 6.789 moles of NaCl per 1,000 milliliters. 3 significant figures, 4, the 1,000 is the exact number. When you multiply and divide, you get the same number of significant figures in your answer as the number with the fewest, which in this case is 3. So my answer has 3. In this multi-step problem, you can either round off at each step or at the end. As I've said earlier, I'm a round off at each step person, but I calculate both ways, and either way will be the same. If they're different, will be correct. So now in step 2, we want to get to grams of NaCl. We have moles of NaCl. So we have 2.34 moles of NaCl. We want to get to grams of NaCl. Use your good buddy, your good friend, unit analysis. Whatever we're trying to get to goes on top of the ratio. Whatever we're trying to get rid of goes underneath. I forgot to write NaCl, but you get the picture. This cancels out. I'm left with grams of NaCl. Now, where do I get this relationship, 1 mole of a compound to grams of a compound? Well, in case you forgot from test number 2, 1 mole of a compound, this is important information. Test number 3, you'll be given this, is equal to the molecular weight of that compound in grams. And the molecular weight of that compound is the sum of all atomic weights. So we need the molecular weight of sodium chloride. And here, 1 mole, the molecular weight equals a gram in grams. 1 is the sum of all atomic weights, 1 sodium, 1 chlorine, and the 3 significant figures. Sodium is 23.0. Chlorine is 35.5. Add them up, you get 58.5. Remember, when you're adding, you get the same number of significant figures to the right of the decimal as the number with the fewest significant figures to the right of the decimal. In this case, they're both 1, so you don't have to do any rounding off. And we put 58.5. It's 3 significant, 3, the 1 and 1 mole. It's the exact number. And my answer should have 3 significant figures. Remember, if you don't have proper significant figures, I take off a point. You can lose some serious points if you don't do it. So please do. And it turns out, if you round off at each step, like I do, or at the very end, you get the same answer. And with that, I'm done. That's the review for test number 3. Make sure you try some of the practice problems, for each chapter so you do good on test number 3. And the advice I gave earlier, show your work. If any of those bigger problems, you made a mistake, say you pressed the wrong buttons on your calculator, you show no work and you get the wrong answer, like really wrong, it's supposed to be 275 and you put 109, I give you 0 points. But if you show your work and I said, oh, that person didn't know how to do it, they just pressed the wrong buttons on their calculator, I'll only take off 1 point out of, say, it's an 8, 10, or even 15-point problem. Instead of getting 0 points, you'll get almost all of them. So it pays to show your work. One last thing, don't forget hand in labs. After 1 week late, you get a 0. Labs are easy points. They're not that hard. So, but you got to hand in the labs and upload them to Blackboard. And with that, remember this Thursday morning, I'll be sending out the email with the password for test 3. So I have until Friday, 8 p.m. to upload it as a single PDF file. Please don't be late. I'm going to be taking off late points if you are on that announcement. And don't forget, tomorrow I'll have my office hour from 7 to 8. If you have any questions, come on by. Unfortunately, once in a while, Zoom gets me. It got me. I'm not going to explain why. And I had to redo the office hour login. I sent out an email with the new login. sometime tomorrow, I hope I'll change that in the syllabuses if I have a chance, and also on the widget on Blackboard. And with that, I'm done. If any of you have questions, hang around afterward. If not, I'm going to say "Gang gesund." Remember, that means go in health in Yiddish. And it's still dangerous out there. I still wear a mask with a few people. And I'll say bye now. I stole that from Granny and the Beverly Hillbillies. Bye.